This is a video for MEI Core Pure Mathematics, Sequences and Series 3 Maclaurin series, 3.3 Maclaurin series of standard functions. We've already seen how functions such as e to the x, sin x and cos 2x can be approximated by a polynomial using Maclaurin series. We've seen these two plots before. Here's e to the x and here's a polynomial approximation for that. And here's cos 2x, and here's a polynomial approximation for that. There are many other functions that also have Maclaurin approximations, some of which are quite standard, and we use those quite regularly, and we'll look at those in the next few slides. You need to be familiar with the following. So e to the x has this series expansion. This is the Maclaurin series for it. And that's valid for all x. Notice the general term, x to the r over r factorial. And if you can remember the general term, generally you can construct the series for yourself. This is log of 1 plus x. So here we've got alternating signs, and then the general term is just x to the r over r. And again, if you can remember the general term, then you'll be able to remember this series relatively easily. Notice we've got a restriction in terms of the validity of this series. X has to be greater than -1 and less than or equal to 1. The less than or equal to 1 is to ensure that this series converges, and the greater than -1, well, if x was -1 or less, we'd be trying to find the log of 0 or even a negative number, which we know is undefined. Series for sin x here, notice again we've got this alternating signs, and we've got just odd powers, and in fact sin is an odd function. It's valid for all x, but remember x needs to be in radians. A similar sort of series for cos x. Again we've got the alternating signs, and we've just got even powers, and we know that cos is an even function. Again valid for all x, and again x needs to be in radians. And finally for this we've got 1 plus x to the n, and this is just a binomial expansion of 1 plus x to the n, and this converges provided mod x is less than 1. So there's all of them written up for you on a single slide. You need to be familiar with these, which means that you should remember them, you should learn them and be able to reproduce them, and certainly you don't need to derive them, you can just quote the result. In general, if you can remember the rth term, you can pretty much establish the series from that. And don't forget, there are restrictions on some of them for the validity of these series where they don't converge outside of that range. So let's have a look at a couple of examples. Here we want the Maclaurin expansion up to the term in x cubed for e to the -3x, and we've been given here the series for e to the x to remind us. So if I want e to the -3x, well, it's just this blob here that I'm going to put into this series expansion. So I'm going to get 1 plus -3x plus -3x squared over 2 factorial plus -3x cubed over 3 factorial, and I can go on generating terms for as high as I like. The next one would be -3x all to the power 4 over 4 factorial and so on. I don't need any more than that because I've been asked for terms up to x cubed, and this is the last term that will have any x cubes in it. So I just need to tidy this up. I'm going to get 1 minus 3x. I'll get plus 9x squared over 2. And then I'll get minus 27x cubed over 6. And this, of course, will just cancel down to 9 over 2. So I'm actually going to get e to the minus 3x is equal to 1 minus 3x plus 9x squared over 2 minus 9x cubed over 2. And that's just up to x cubed. There's a tidier write-up of that. You can see we've plugged the minus 3x into this formula up here, and then worked it through and tidied it up, and that is just for terms up to x cubed. Second example then, let's find the Maclaurin expansion up to the term in x to the 4 for the log of 1 plus 2x, and I've been given here log of 1 plus x to remind me. So let's have a look at the log of 1 plus 2x, and again think about what you've got here. You've just got a little blob that we're going to put in place of the x in here. So that's going to give me 2x minus 2x all squared over 2 plus 2x all cubed over 3 minus 2x all to the power 4 over 4 plus, and that'll keep going. But I'm only interested in powers up to x to the 4, so if we just restrict ourselves up to x to the power 4, we're going to get that the log of 1 plus 2x is 2x. I'm going to get 4x squared over 2, so that's minus 2x squared. 8x cubed over 3, so that's plus 8x cubed over 3. And then this is 16x to the 4 over 4, so that's minus 4x to the 4. And that's where it stops because I'm only interested up to x to the 4. And again, there's that written up neatly for you. There's putting the 2x in place of the x in this expansion. And there's the first 4 terms worked out. So an interesting final question on this: for what values of x is this valid? Well, we know that the blob in the log 1 plus x has to be between minus 1 and 1. So I could write for that 2x, which is the 1 plus something, has got to be less than or equal to 1 and greater than minus 1, which means that x needs to be less than or equal to a half and greater than minus a half. And that's just the confirmation of that for you there. The next and final video in this sequence is 3.4, Maclaurin series of composite functions.